Hello and welcome to the next episode of the Klingberg Wing Mark II development. I'm Raul Klingberg, your host. You may not have seen me for a while because I haven't posted anything, at least anything with me in it. And before I run off to the AirVenture EA fly-in in Oshkosh, Wisconsin, day after tomorrow I go. I'm going to be gone for a week or so, and I thought I should leave you with some things to chew on while I'm gone and let you know what I've been up to for the past month or so. Anyway, today I'm going to talk about my process for building the new outer wingtip panels. Those are the last 6 feet of each wing. And as you know, those wing panels have been through a lot of changes. They're no longer what I consider to be airworthy, so I'm building new ones. And in the process, I saw an opportunity to try to reduce weight. I added those new elevons, which made the glider now tail heavy, statically speaking, and a little more difficult to handle on the ground in terms of pitch. You know, it tends to go tail heavy on you like this. So I need to get a couple of pounds, maybe 3, out of the 2 wingtip panels. Now, each wingtip panel only weighs 6 pounds. So to get a pound or more out of 6, not an easy feat. And it requires a total rethink of how those tip panels are built and tighten the screws on the engineering and the building that went into them to get all the weight possible out of them. And that's what this video is going to be about. It's going to be relatively long. I could cut it up into segments, but I'm sure they wouldn't be the right segments for you. So I'm going to leave one long video and you decide where you want to pause and do something else and come back and see the rest of it. And I hope it's useful for you. Hope you learned something along the way. I know I've learned a lot. So hang in there with me. Maybe you want to take a break right here, go get a beverage and a snack, and kick back and see what I've been up to. Okay, so welcome back. I hope you're settled in and are ready for some engineering analysis. We're not going to do any math, but I'm going to do a lot of talking about trade studies. Trade studies are the bane of a lot of engineers because it seems like you're going in circles, and it seems that way because you are. It's a looping process. It's an iterative looping process to try to get to an optimum solution. And it takes time, and it can be frustrating at times, and you get unknown results. And getting to success, both something that'll work and is actually delivers all the performance you want, that can be tough. I've spent most of my career in engineering as a systems engineer, which by definition is a person that deals with iterative loops a lot. So it's normal territory for me. And I find it fascinating to diddle with all the little parameters and figure out how to balance them out to get a better solution. And that's what I'm going to talk about here today. So if it sounds like I'm talking in circles, it's because we're going in circles. We're iterating onto a good solution. And I'm going to talk about several items in terms of lightweighting the wingtips, but I'm going to focus in 2 areas, and that would be the ribs and the D-tube/spar. Once they're bonded together, the D-tube and spar are kind of one and the same thing. And I'm going to talk about what the weight drivers are and where we can make optimizations to try to get the weight out of the wingtip panels. So let's start off by talking about just the basics of where this trade study starts. And we have to look at the things that we're concerned about are the weight. We want these things lighter by quite a bit. We are somewhat concerned about cost. I'm not independently wealthy. I can't dump $1 billion into this. Buildability, it's of no good to anybody if we can't build it. And durability. Now, durability is kind of last on the list, but important. If people are to find this to be a popular method for building aircraft, it's got to be durable. It's got to last. It's not strictly an experimental aircraft. So we put durability on the list, but we'll sacrifice some durability for other factors when needed. Now, we're talking here about just composite aircraft. That's what this aircraft is. Now, granted, it's got fabric in it. It's got wood, foam, epoxy, carbon fiber, Kevlar, fiberglass. Well, that's the definition of composite. Composite doesn't mean just carbon fiber and foam. Composite is a gathering of a wide variety of materials to create the aircraft. So on composite aircraft, we must remember, in order to do these trades properly, 50% or more of the weight of the aircraft is in adhesives. That's in the epoxy resin, that's in the bonding resins, you name it, it's adhesives. Basically, you have a carefully organized pile of adhesive flying through the air. So if we're going to save weight, we need to focus on the adhesives. It's the easiest place to go overweight. I won't say it's the easiest place to take weight out of the aircraft, but it's the easiest place to go overweight. Number two, in this type of aircraft, ultralight aircraft, the weight is driven by the skins, not the spar or the spar caps. Traditionally, in designing aircraft, everybody's always worried about the spar caps, because that's what carries all the loads. And it's generally one of the heavier components of the aircraft. And if you can save weight anywhere, you'd save it in the spar. And I've had many people write comments to my YouTube videos saying, oh, you did this and this and this, and that's not optimum for the spar. Well, I don't care if it's not absolutely optimum for the spar, because the weight's in the skins. A lot of people don't get that. A lot of people don't understand. But yeah, the weight's driven by the skins. It's a large area. It might be thin material, there might not be a lot of it there, but it's a huge area and it adds up. So we got to keep an eye on this factor, the skins. Number three, secondary bonding. Anytime that you mold a part or make a part out of composites, and you got another part over here, and you put them together, you got to bond them together with something. That's called the secondary bond. That's after the components are already cured, and you have to join them together. Secondary bond. Secondary bonds add a lot of weight, and it's sneaky. You don't realize it's happening. You know, so I'm just going to glue these together. But every little bit of glue or epoxy or bonding agent that oozes out around the corner is wasted. Those fillets, the little blobs, here and there, a little bit of this, a little bit of that. So I'll fill it with microballoons. Oh, even then it adds up. We don't want to have any more secondary bonds than we need. So the secondary bonding can be a big driver. And if you're a home builder, it's highly variable because people put stuff on there with a brush or a stick, and human hands are not very consistent. And sometimes you get more adhesive, sometimes you get less. The stuff that oozes over the side, you go, oh, I'll just get in there with a paper towel and wipe that stuff up. And after a while, that gets really tiring, and you stop doing it, and you get a lot of buildup of epoxies that aren't doing anything. So, and then a fourth factor is factory built versus home built. When you're factory built, you can eliminate a lot of the secondary bonds by doing what we call co-cure. I'm going to build the spar and this other thing at the same time in a mold. And it's going to be one long layup. I'm going to go in an autoclave, so I have pre-preg fabric, and that pre-preg fabric will stay nice and soft all day long while I lay up all of these little itsy-bitsy pieces and shove it in the autoclave, and boom, out comes a wing. You can't do that at home. You don't have an autoclave. You can't deal with pre-pregs easily. I know some people do, and pre-pregs are advancing in terms of their adaptability to home environments, but it's not an easy thing for a home builder to deal with. So the home builder is highly variable, and you can get higher weights. However, you can do other things with it. The factory will have fewer secondary bonds, but the home builder can tailor the materials. A factory is not a good place to have balsa, plywood, styrofoam, fiberglass, Kevlar, graphite, foam, PVC foam, styrene foam, a dozen different materials to build one aircraft. Factories hate that. I want 3 materials, and I'm going to use 3 materials in the entire aircraft. I'm going to control my inventory that way, and I'm going to reduce complexity for my factory workers. But that means that you can't optimize for weight as easily. If you can vary your materials all over the place, like, this part here, I could make that out of wood. and I know the wood's going to have a higher strength to weight ratio because I can get the right thickness, right size, and all that. Oh, it's inexpensive because other people manufacture it in huge piles of it. It's cheaper than carbon fiber that I have to make. Oh, and it's not brittle. Um, so Rick, wood's great. I'm going to use wood here. Well, if you're at a composite glider factory and you said, oh, all of these parts have to be made out of wood, and you got to have a guy there with a knife, and he's going to cut these things, or you got to go on some kind of jig and cut them out, and they're going to glue them in one by one by one by one, and it's going to look like an old-fashioned aircraft factory, which was more like a furniture factory. Lots of sticks and shavings and sawdust, and highly skilled workers. In modern aircraft manufacturing, that's just a no-no. You'll be out of business in the blink of an eye. It's hard enough to make money in the aviation business, let alone shoot yourself in the foot with a lot of different materials. So factories are not, they lack the tailoring of materials. A home builder can tailor all the materials because their time's free, right? At least that's what people tell me. Your time's free. So you can do all of that extra work to keep the weight down. So with my glider, I'm trying to hit somewhere in between. I'm trying to create a design that could be factory built, also good for home builders. And generally what that means is that some components would be factory made, like a D-tube and spar combination, and the guy that purchases the kit gets his D-tubes and spars all bonded together and ready to go. He sets up the jig at home, and he does the job of building up the ribs and gluing them in place and putting the fabric on and all that detail work that would use up too much factory labor. So I'm trying to hit that kind of happy medium in between them. So that's what we're looking at in terms of materials and how you build the thing, how it all goes together. This is our trade space, is what we call it. Now, other issues that we have are margin on margin and minimum thicknesses. And these are tricky items that will sneak up on you in the middle of your design and shoot you down. The margin on margin is a classic engineering problem, especially if you have a large group of engineers. Every engineer does his job like he's supposed to do it, calculates the strength of what he needs in terms of strength for that particular component, then he designs it to that strength, and then he adds engineering margin to it, as he should, just to be on the safe side. But then if he's working at a large company and he likes to keep his job until he gets to retirement, he might sneak in a little bit more margin there because, by God, it's not going to be his part that fails, be the guy sitting next to him. He's not going to ruin the mission because of his part. And these become hidden margins. Now, in a project like mine where there's one engineer, it still happens. I've been known to sneak in extra margin when it's not needed. Just because, I don't want it to break. I don't want it to fall apart. I don't want to die in the process. So margin on margin becomes an issue. And we have margin buildup over time. I have margin on the D-tube for this, and I have margin on the spar for that. But wait, they get bonded together into one tube. That's why we call it a D-tube. And why do they both have margin on them? Why don't I calculate it as a combined structure and apply the margin of the combined structure? Well, for a guy like me that doesn't have a lot of high-end analysis tools, the easy way to do it is to do it component by component, the traditional methods. And I'm an older guy, so I'm kind of stick with the traditional methods. But you end up with margin on margin that way. And we're going to have to try to eliminate those. In other words, we need to do better engineering to get the weight out. So, and then the other one's minimum thicknesses. We're dealing with an ultralight aircraft here. Really, really light. Half the weight of the next lightest standard class sailplane out there. Less than half. There are other ultralight gliders out there that are in this size range. They weigh 250 pounds. The only other ones that I know that are in this weight range are the Swift and the Aerooptrix. The Atos sort of comes in. It lies somewhere in the middle because it's got a composite D-tube and standard hang glider fabric trailing edge. So it's in that no man's land in between. It's hard to compare them. But on aircraft that are built like this, for these weight ranges, you're down into minimum thicknesses on the skins and so forth. What happens is we get down to one layer of cloth. And one layer of cloth's plenty strong. It'll carry all the bending loads or torsional loads, and you go, oh, good, I'm good to go. One layer of this, I'm done. And then all of a sudden you discover I have durability issues. It dents easy. Well, in composite aircraft with stressed skins, dents are a big no-no. A dent is a buckle in the skin, and a buckle's where it's going to fail. You cannot allow the skins to have a buckle in them. If the loads get high enough, it'll fail right where that dent was put in the wing. So dents are bad. Some worse than others. You got a crease in the skin that's running span-wise, less of a problem than one that's running cord-wise, especially on the lower surface. So durability is an issue, and we have an aircraft that has to be taken apart and put together every time we go out to fly, and it goes through a rough and tumble life. So it's got to withstand a lot of handling, and that's when you can get dents and so forth. And I'll testify to the fact that the main sections of my wing have a lot of little dents in them. Nothing critical. I got a couple of them. Some I've repaired, and some are due to be repaired. But it's problematic, and I don't think most owners or home builders would want to have that type of problem on their hands, where every winter you're out in the garage filling and patching and making it good for the next season. That's not something we really want to do. And if we just add to the thicknesses to make it durable enough, then it's too damn heavy to pick it up and run with it. So it's a tricky area. Probably the best solution, which I'm going to talk about later, is the Swift and how they used Kevlar to make their wing skins. And it was really a brilliant solution at the time, and to this day, still a brilliant solution. We'll talk about that later. So let me talk about some of the things that I've been doing lately to study what's the optimum way to get to lower weight. And I did an extensive study of the ribs and how they're constructed. And I'm going to gather up some of my samples here. And I did a lot of them. This isn't all of them, but this is a good portion of them. Let me get this one over here. I'll have this as a standby. Okay, so as you know, I have ribs that look like this. It's a 2 pound per cubic foot blue styrene foam, and it has wood cap strips. I have data, and I've made that available on Patreon on how incredibly strong these ribs are. Built up ribs out of spruce sticks, half the strength of this. Plywood ribs, 3/4 the strength of this. If you don't put any holes in the foam and the cap strips are glued on here, well, these are really, really strong. So you can build them really, really light. So that's how the ribs are built. Now, where's the weight in the rib? Where's the weight in this rib? Well, it's not really the foam, is it? Foam weighs next to nothing. But we have wood cap strips. The density of the wood cap strips is about 60, 65 pounds per cubic foot, something like that, I think, if I recall correctly. And we have adhesives. We have secondary bonds of gluing the cap strips to the foam. And let me tell you, you can waste a lot of adhesive in that area, as I know well. So I decided to start looking at how do I reduce the weight of the cap strips and the bonding mechanism between the cap strips and the foam. First thing I looked at was, I got a bunch of this pre-cured carbon fiber strips, right? Oops, there goes one. We'll set that aside. Anyway, so I'll just glue this to the foam. Carbon fiber is incredibly strong. It can really take the loads. You're pushing up and down on the trailing edge of the rib. Carbon fiber will carry way more loads than you need. Margin on margin. It'll carry more loads than you need it to carry. But got amazing strength to weight ratio. Easy to make. I can make up a big sheet of this stuff and cut it into strips. Okay, so let's try that. So I tried 2 methods for attaching it to the foam that I thought would be very efficient and do a great job. Actually, I tried 4 different methods. So first one I tried, I had high hopes for this. was 3M VHB transfer adhesive. Now I know that this, let me set these down. I know this looks a lot like tape, regular tape, but it's not. This is just a liner, and on the inside is adhesive. You can't see it on the camera, but there's an adhesive in here, incredibly strong. They have versions that go to really high temperatures, and you apply this to one side, peel off the backing, stick the parts together, you're done. No wastage, nothing running over the edge, no cleanup, don't get your hands gooey. It's really great stuff. It's used a lot in the electronics industry. Well, what are its drawbacks? Well, it's bloody expensive. One little reel of this stuff's like $80. But this is the aircraft world, you know, and sometimes we pay a lot of money to get the performance we want out of our materials. So I went to experiment with it. Now, I've used this in the past to put smoothly finished composite parts together, like graphite panels. And wow, it works great. They are just permanently bonded together, especially after about a week. It takes about a week to set up on this stuff. I say set up, but the bond gets better over time. So I tried using this on the urethane foam with the carbon fiber cap strip. And I could not get this stuff to bond well to either surface because these surfaces aren't really, really smooth. And there's just not enough bond area. So that pretty much killed the tape idea. And I heaved a sigh of relief because it's so darn expensive. So there we are, right there. Okay. So let's try something else that's easy to apply and you don't get too much on there. And that would be spray adhesive. 3M makes a variety of spray-on adhesives. This particular one is compatible with PVC foam, but not with the styrene foam that I'm using. You would have to use 3M77 for that. But this is great because you can spray on one even layer of adhesive. You could set up all of your rib cap strips and cover them as a group and then stick them onto the ribs. You'd spray a little bit on the ribs because it's a contact adhesive. You let the two sides dry most of the way and then slam them together. And don't miss because you only get one shot at putting them together. Don't make them crooked. And when it dries, it's really quite lightweight. Well, it turned out to not be any lighter than like epoxy. I was like, what the heck's going on? I was very careful on how I applied it. And you know what happened? The spray width, right? You got a fan spray and you're trying to spray it on the rib. And if you don't put protective tape on either side, you get overspray that goes around the rib like this. It just comes down from the top, goes on, and you get all this excess contact adhesive on the sides of the rib that add a bunch of weight that's not doing anything. And I was very chagrined about that. I thought, oh my God, I'm just going to have to put tape on all the ribs while I spray and then remove the tape. Well, that doesn't fit within the buildability category here. That's just a pain in the butt. So spray adhesive out, despite its low cost. So where does that leave me? That leaves me with traditional bonding methods. We have epoxy and urethane adhesives and just about any other adhesive you like to think of. We could use wood glue, but I've discovered over time, I didn't even test it here, wood glue, good carpenter's glue, sticks great to the wood cap strips, of course, but not to the foam. Foam's a plastic, and it just doesn't like to adhere to the foam very well. So I was down to epoxy, and I didn't bring any samples in here, and urethane, like Gorilla Glue. Urethane adhesives are pretty cool because you don't have to mix them. They're compatible with almost all materials. They're not going to melt any of the foam, and they're really strong. In fact, some of the tests I've done, the bond with the Gorilla Glue is just as good as you would get with epoxy, at least for what we're doing here. Now, how do you get those adhesives on the rib so you don't have too much, so it's not oozing out the sides, and you don't have to go back and wipe it up, and you can put it on once and bond them together? Well, it took a while to dawn on me, but then I realized, oh, carpenters, furniture builders have these things. They have glue applicators that are a roller, an inking roller. Fill this up with glue, give it a little squeeze, get it layered on the roller, and then we can run the roller down the rib like this, no excess running over the edges, just on the surface that you need. No cleanup to do. You get that on there, put your wood on here, put a couple pieces of tape over it. If it's a cap strip, it's curved, we gotta hold it down. And that goes on nice and clean. You can do the same thing with epoxy, but then you can only use this once. But they're pretty cheap, you know, $3, throw it away when you're done. So that turned out to be a very clean method for applying adhesives. And then I went into a round of testing of cap strip materials and the dimensions, the basic setup of those materials. Now, if you remember, on my original ribs, I had 3/4 inch wide basswood cap strips, 1/16 of an inch thick for the wingtip panels, 3/32 for the inboard panels, 1/2 inch thick foam. And these were glued on top like this, right like that. And that's very traditional. You get a little I-beam shaped rib, really strong. Well, it's ripe for excess adhesive on the back side here, where the wood hangs over the foam. And you tend to get a bead of glue in there that's just a wastage. It doesn't make anything stronger. And I thought, oh, why don't I make the cap strips so wide? You know, it's like, well, I'm an old-time model airplane builder from, 50 years ago. And, you got a skinny little balsa rib and you put a cap strip on it. The balsa rib isn't very strong side to side, so we put these nice cap strips on it and it stiffens it up. You make a little I-beam rib and it's nice and stiff side to side. Well, is that really needed here? Have to stop and think. Gosh, is it really necessary? This goes back to this margin on margin thing. Don't overbuild. Just stop overbuilding. What's really needed to do the job? Do I need 3/4 of an inch or will 1/2 an inch do the job? So I made up some samples. I don't have them here, but some had wider caps and some narrower caps like this. And this was strong enough, not as strong as this, but strong enough and much less adhesive involved in attaching them and less weight in the cap strip itself. So the conclusion was, don't make the cap strips any wider than the rib material. So how wide does the rib material have to be? Well, you might be able to go down to 1/4 inch. These are 1/2 inch. You probably might be able to go down to 1/4 inch or 3/8, something like that. But I didn't test that, and I didn't test it for a pretty darn good reason. I don't have any in stock. I've tested stuff of materials that I have in stock. So we're stuck with that for right now. So, and you're wondering, well, what about the side-to-side stiffness? And I go, well, it's good enough. Oh, there goes that one. See, got a couple of buckles. That's how they fail, side to side. The adhesive fails, the graphite pulls away from the foam, and you have a failure. But you know what? In this type of aircraft, that's a very low probability of happening because we've got this stuff. Fabric. This is a fabric covered wing. We got this polyester material with adhesive on it, and this stuff is glued to the ribs. The ribs are underneath here. Fabric's glued here, and it goes from rib to rib to rib to rib. Well, there's your I-beam. Look, it's right there. It's I-beam. And the top part of the I-beam is fabric. Now, it can't take compression, but it can take a boatload of tension. And the fabric is shrunk tight. It's glued to the ribs. These ribs can't go sideways. You got one piece of fabric that's pulled tight. The ribs are glued to it. Well, the side-to-side loads don't have to be carried by the cap strips that are on the rib. It's carried by the fabric. What if the fabric fails? Well, then the loads go into the cap strips. But if you get the fabric failing in flight, you got bigger problems on your hands rather than these little cap strips failing. So, margin on margin. Got to take under consideration that the fabric covering is a structural material and can take loads, tension loads. It's lousy at compression loads. And by being able to take tension loads, these ribs can't go side to side. And a rib failing along this bond line along its whole length, impossible. You might have a small failure, you'd see it, you'd fix it. So we got to include the fabric in the strength of the ribs. And when you do that, oh, well, I don't need those really wide cap strips. In fact, I don't need thick cap strips. I can use really thin ones. I could use, there's a thought. Hey, here's something I remembered while I was trying all this stuff out. The PVC foam. Much better compressive strength than the blue styrene. It's really pretty darn good compressive strength. Reasonable tensile strength, especially if it's got the fabric over it. This fabric is incredibly strong in tension. You can never pull it apart. Do the cap strips really need to take all those tension and compression loads? Well, they need to take some compression loads because the fabric can't do that. But they really don't need to take any tension loads. You put it all in the fabric. Okay. And foam glues to foam really good. They become essentially one piece. And I learned in working with this stuff that the PVC foam, the Airex, I can iron that fabric onto this without melting this foam. This foam will resist temperatures in excess of what's needed to apply the fabric. Well, that's pretty cool. It's relatively inexpensive. It's pre-made in a sheet. You can cut it into strips. You can stick it on here with either epoxy or the urethane glue. And wow, look at that. You got essentially a rib with cap strips, but the cap strips are foam. And at first thought, you think, oh my God, you can't have foam cap strips. And I'd say, why not? And that's another thing you always have to ask in these trade studies is why not? Why would you not do that? If it's strong enough, right? Cheap, it's affordable, it's buildable. Well, durability, last guy on our list. What happens with this stuff is the PVC foam has great compressive strength compared to the blue foam, but not compared to wood. You could dent this stuff so easily. Just dent it like that. You run into a rock or something like that. Now it's got a dent in it. And then if you put a load on it, that's right where it's going to fit. That's a problem. You buckle these surfaces, you don't have a strong part anymore. The wood, on the other hand, put some wood on here, it's next to impossible to dent it with a rock. Now you could bang into a rock and crack it, then you'd want to go fix it. But in terms of the normal handling and transportation stuff, getting dents in the wood doesn't happen. It doesn't dent. So the foam was out. Unfortunately, it would have been really light. It's the lightest weight material. It meets all of the strength requirements when you add the fabric to it, but it didn't meet the durability requirements in terms of it dents and can fail easily that way. So now we're back to other materials. And basically what we're down to is some composite material like carbon fiber and wood. And it could be plywood, it could be balsa wood, it could be basswood, picklewood, it could be spruce. So carbon fiber. Everybody, carbon fiber is the answer to everything. It's a miracle in aircraft construction. And I would say, not necessarily so for ultralight aircraft. Just because it's incredibly strong doesn't mean that its strength to weight ratio is appropriate for what we're doing because of the minimum thickness problem. You get down to what, I don't need these phenomenally strong rib cap strips because I'm putting some loads in the fabric. I only need one layer. One thin layer of unidirectional carbon fiber would carry all the bending loads that I need to carry and the side-to-side loads and all that stuff. And easy to make. I can lay up a big sheet of unidirectional carbon fiber flat, use a razor blade to cut it into strips, quick and easy, done and done, and then glue them on the foam. Yeah, pretty slick. And it leaves a nice smooth surface to bound the fabric to. Even better. However, much to my chagrin, the carbon fiber did not pass the durability test. It has almost the same problem as the PVC foam. It dents really easy because it's so thin. We're down to minimum thicknesses, one layer. It's so thin, it dents so easy, and the blue foam doesn't have that much compressive strength. Now, if you made this rib out of something that has higher compressive strength, well, then it's going to weigh 6 pounds per cubic foot instead of 2, like I have here. So then the rib gets too heavy. Well, you need high compressive strength at the surface only so that the carbon fiber doesn't compress. I could take the PVC foam, just like I did, and put little strips on top first and then put the carbon fiber on. So the carbon fiber would be protecting the PVC foam from getting dents in it, and the PVC foam would provide enough compressive strength to where the carbon fiber doesn't get dented. Now I've got 3 materials in there. And I got 3 processes and 2 secondary bondings. And in terms of strength to weight ratio, it doesn't play out. And if the carbon fiber gets dented, it is brittle. It doesn't just dent. When it dents, it cracks too. And then you get one of these. You get one of these failures. This was a compressive failure. I dented it like this with my thumbnail, and you bend it like this, and boom, that's where it fails. Just like that, right where I dented it. Happen every time. Oh, well, let's go back up to cost here. See, this is where we're going through those costs. Carbon fiber is bloody expensive, and along with the epoxy and everything else. If you go look at the prices on this stuff, yeah, it's easy to work with and all that stuff, a high strength to weight ratio, and yada, 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 yada. But it's bloody expensive compared to wood. They make oodles of this stuff. And so what's the best one to put on here? Well, we want to have dent resistance. We want to have something that's durable outdoors, wide temperature and humidity conditions. And we want stuff that's readily available. Buy it anywhere, practically. You order it. And it's cost effective. Well, aircraft plywood, thin aircraft plywood, been around for decades and decades and decades. And they make tons of it. And you know what? It's about 2/3 the cost of the carbon fiber. Wow. And this is made with waterproof glue. It's made to go in aircraft. It's meant to go outdoors if you need to. Very easy to bond to. I mean, this stuff has been specifically designed for the construction of aircraft. Really high strength to weight ratio, lower cost, resists denting. It doesn't leave a dent. Wow, easy to work with. Cut it with scissors. Cut it with a razor blade. And you know what? On the carbon fiber, I'd have to lay it up first to make a sheet of it and then cut strips. This stuff's cool. They send you a sheet of it already made, and a sheet that costs 2/3 the cost of the carbon fiber. Why wouldn't you use this stuff? You would never pass it up. Oh, I'm building a composite aircraft. I'm not going to put wood in my composite aircraft. Well, if you want it to be really light, you should give it serious consideration. And that's why I have basswood on my current cap strips. But basswood is a little susceptible to humidity variations, expansion and contraction. This plywood is not. So then I had to go do some studies to find out which is really lighter. It turns out that 1/64 inch thick plywood, that's a 1/2 inch wide, is the same weight as my 3/4 inch wide basswood. So, stronger, easier to build, no excess adhesives building up around the corner. And as I went through and did all my studies of all the different variations, and I did a boatload of them, this guy right here, 1/64 inch thick plywood on blue foam with urethane adhesive applied with this roller, high strength to weight ratio out all of them. It's the answer. It's the correct answer. So by going through parametric studies, thinking through it, and how the aircraft is actually used, composites are out for cap strips. And foam is out for cap strips. And plywood is fabulous. So I'm sticking with that. That's how you end up at wood cap strips. Somebody might come in and put in 16th inch thick basswood here, 1/2 inch wide seams of foam. And it might be a little lighter. It's not going to be as strong, and it won't be as durable for various weather conditions. So use the stuff that's actually made for building aircraft. Use the aircraft plywood, 1/64 of an inch thick. And that's how we end up at the solution. And surprisingly, urethane glue, just about as strong as epoxy for this type of application. It's always the foam that fails. And the urethane glue is slightly more expensive than epoxy. I know that's hard to believe, but it actually is. I went and looked. You can't buy 5-gallon buckets of it readily. It comes in much smaller containers. So there are some drawbacks to it, but the urethane glue is lighter every single time that it's applied. Epoxy is heavier than the urethane glue. And the urethane glue is entirely waterproof. It's great. So applied with urethane glue, not epoxy. Don't have to worry about mixing in microblues to make it all lightweight and stuff like that. Don't have to worry about working fast. You know, oh, it's going to cure in an hour. I got to get going. urethane glue worked out to be terrific for applying the cap strips to the ribs. So that's where I'm going. The ribs on the new wingtip panels are going to be have 1/2 inch wide, 1/64 inch thick cap strips applied with urethane glue and a woodworking roller. That's simple. And the other thing I'm doing to save weight, another big thing, I decided that given that the D-tube goes to the 30% accord, and that's about 75% of the aerodynamics, the aft portion is not that critical on aerodynamics. I don't need to have it that flat and smooth. I can live with a little bit of potato chipping. So I'm taking out half the ribs. Instead of having 1 foot rib spacing, I'm having 2 foot rib spacing. And we're going to call that good enough. So maybe a little tiny sacrifice on aerodynamic performance and save 4 or 5 ribs. I'm probably going to save a 1/4 pound on each wing panel, just on the ribs alone, 1/4 pound or more. And if we want to save a pound, well, that's a long ways towards the goal. So more efficient cap strips on the ribs, fewer ribs, and probably save maybe upwards of 1/3 of a pound, just in that area. So that's the answer for that. Now we have to look at wing skins. And okay, before I go on and talk about wing skins, let me mention the spar here. This is a spar that I made up earlier for the new outer wing panels. And this features a 3/32 of an inch thick shear web here with Kevlar on each side. There's 1.8 ounce Kevlar on each side, one layer. Made up in a big flat sheet so I could cut the shear webs out of the sheet nice and easy. And then I applied spruce, or just about any, this happens to be pine, cap strips to the shear web for rigid support for the real cap strips, which are the carbon fiber here. This is the pultruded high tensile strength carbon fiber. Runs along the top. And then by the time you get out to here, there's enough strength just in the wood to carry the loads. And then I have the same type of wing attachment fitting that I've been using previously on this end, and it's bonded to a plywood core here. And this is a great example of the margin on margin issue. There's a bunch of things I did here that just make this really easy to build, but it's also considerably heavier than it needs to be. I think this weighs almost a pound here, and it really should only weigh at most 3/4 of a pound, maybe more like a 1/2 pound in order to carry the loads. One of the main issues of this margin on margin is traditionally with aircraft, especially home-built aircraft, sailplanes in general, the designer comes in and he says, oh, I'm going to stay extra safe by assuming that the D-tube or the wing skins don't carry any bending load, and that all of the bending load is carried by the spar caps, and that the skins or the D-tube only carry torsional loads. And they design each one to do that job. The facts of the matter is that the skins or the D-tube can carry tremendous bending loads because of their shape and the materials that are applied there. And generally, by the time you get down to minimum thicknesses like we are in this with this aircraft, the amount of material that's on there in one layer is enough, maybe enough to carry the bending loads, and way more than you need for the torsional loads. So if you design, like I did here, cap strips carry the bending loads, D-tubes only for torsional loads, well, the D-tube's way overbuilt. And it ends up that way because the D-tube ends up being built for durability. We're down to minimum thickness. We don't want it to dent too easy, do a bunch of things to prevent that. And it's way stronger than it needs to be for torsional loads, especially out at the wingtips. Because out at the wingtips, how bad are the torsional loads? They're very low. Torsional loads are at the root end. That's why I have the wing fully skinned at the roots to help take the torsional loads. So the wingtips were considerably overbuilt for a variety of reasons. And then this type of setup has a lot of secondary bonds. Shear web is laid out first, glue on the wood cap strips, then glue on the carbon fiber cap strips, then glue in the root fittings and this fitting and overlay it, and a lot of secondary bonding. There's a lot of adhesive in this thing That's probably not needed. So what I'm doing right now out in the shop, I'm building a mold so that I can mold spars for the outer wing panels. They'll be much lighter. It'll be essentially the same setup, 337-inch foam with Kevlar on each side, but it's going to be wrapped. It's going to be wrapped around a mold like this, so that the shear web and caps are molded at the same time, very much in the same way that I did the spars for the main wing panels. And if needed, I will put in unidirectional carbon fiber between the two layers. The first layer is going to be the inside of the shear web, and it's going to go like this, and then the foam will go on it, and there'll be a layer that goes over the outside. And when I put on that second layer, I can put in some unidirectional carbon fiber if I need to. And then I'm going to do the root fitting a little bit different. I'm going to put in a high density foam instead of plywood here at the root. Why'd you use plywood the first time around, Raul? Well, I'll tell you, habit. My first wing, which worked out great, I used plywood to do this job. Never had a failure, worked perfectly. So I use it again. Fact of the matter is, plywood's not really needed. My first wing, I used plywood because I had bolts through here. This fitting was held on with bolts, and there were bushings in it. And the loads, in fact, the root fittings, I don't think I even bonded those on. I think they were just bolted on. The carbon fiber fittings that were bolted on. So, no bolts here. Well, then you don't need plywood. The plywood was in there for its pull-out strength, so that you don't shear the bolts right out of the core material. And made perfect sense in that case. And I did it here out of habit, but there's no bolts in here. The shear loads are put into the skins and then get distributed into the shear web like this with this overlay. The bond area of this fitting alone is enough to take all of the loads. And then this overlay is margin on margin. So the root fitting is going to be done differently. Initially, I thought that I'd put in the high density foam core here that's a 1/2 inch thick at the same time that I do the layout. But the complexity of the mold was too high, and we ran into the buildability issues. I'm not a factory. I'm still a home builder. So that's going to be a secondary bond. It'd be a relatively small area that's a secondary bond, and we'll just have to live with that. But we're getting rid of the wood, getting rid of the secondary bonds out here. It's all going to be done in one layout. And then this root fitting here is probably way overbuilt. And I'm going to take a second look at that. It certainly is, because this is all one piece of carbon fiber, and then I cut out these notches. And I'm probably okay if I just go with a strip of this material, and as I come back, flare it out like this, and just lay this up differently. Lay these up as individual pieces on a mold, on a throwaway mold, where they're this thick at this end, and then they flare out like this for more bonding area. And then this area will be filled in also. So I'll be able to distribute the loads out into the spar from these end fittings and eliminate this material that's in the middle here. And that's probably an ounce, 1.5 ounces, something like that. Nominally, you'd say, what's an ounce? What's 1.5 ounces? Well, you do this 3 or 4 times. Oh, 1/4 pound, 1/2 pound, and I'm looking to save a pound. So don't overbuild. No margin on margin. So the spars, even though I already built these, done, I could build the wing up out of these. These are going in the, well, it was interesting pile. And maybe we cut them up later and use them for parts. We'll pull out samples and use them for testing. So a little bit there. So a little bit there about the spars and how I'm going to do them different. You'll see a video coming up in the future after I finish those new spars, so you can see what they look like and how they came out. Now, let's talk about the wing skins. I have an old D-tube here that wasn't any good. I keep it around for these demos. Carbon fiber on the inside, fiberglass on the outside. This is about 3 ounce. What was this on the inside? No, that's about 2 ounce. This is the 2 ounce spread toe carbon fiber on the inside. Very expensive, about $95 a yard. Inexpensive, $8 a yard fiberglass, $120 on the outside. Satin weave. very smooth finish, great stuff. I think it's about 3 ounces a yard. And then unidirectional carbon fiber in the leading edge for impact resistance, which works great. You can't dent this stuff. Now, on my main wing panels, I've been getting a lot of dents in the surface. The fiberglass is susceptible to denting. And I've done a video on this in the past and looked at different layup techniques to avoid that denting. And turns out the Swift is about the best answer available. They have one layer of 1.8 ounce Kevlar on the inside and 2 layers of it on the outside. So they're almost the exact same weight I am here. They're a little bit heavier on the outside, a little bit lighter on the inside. Kevlar is all that's needed. And by the way, Kevlar tensile strength is very close to that of carbon fiber. In terms of engineering terms, it's very close. Not nearly as good in compressive strength, but these are the wingtip panels, and the loads are relatively low out in the wingtips. So I don't think the $95 a yard carbon fiber is required. The Kevlar is running about $44 a yard right now, $30 a yard. So half the cost. More cost on the outside, less cost on the inside. Almost a push, not quite. And what am I going to do about the leading edge? Well, when you put on 2 layers of Kevlar, it's about this strong. Not as strong as the carbon fiber, but just about. So it'll simplify the layup. If I don't put this carbon fiber in, we improve the buildability of it, and it should be strong enough. It'll certainly be strong enough. It should be durable enough. We'll see how it holds up on durability. Now, I also have to consider that with the wingtip panels, they're transported in their own nice padded sleeves. And throughout the couple of years of usage of this wing going in and out for testing, I really don't have very many dents in the D-tubes of the outer wing panels, or I haven't had any problems with the winglets. They get transported in their own padded bags. So stuff that's in a padded bag is held up much better than the stuff that's not bagged. Now, to create bags that are 18.5 feet long and 4 feet wide for the main wing panels is, well, that'd be kind of a big deal. And I'm not going to bother with that right now. We're going to go down the path of making the D-tube a little bit more durable. And what I've decided is that despite the Swift's brilliant solution of putting 2 layers of Kevlar on the outside, I'm only going to put on 1, most likely, until I do a little bit more structural analysis, and it might end up being 2. But because it's in a padded bag, 1 layer should be enough to resist the denting. And we'll see. So that's basically how these are built and where I'm going. Now, in terms of optimizing the D-tubes, well, the Swift was done 25, 30 years ago. And gosh, don't we have anything new since then? Are there any new ideas, Ronald? Any better way of doing it? Well, I had to take a look at that. And here we go. I got some stuff in hand right here. I did some reading, found some interesting research that's being done, and I put that research to the test. And what I'm testing here is I ran across an article on additives to epoxy resin to increase its strength and increase its durability. It increases the impact resistance. I says, man, that's just what I need. I need both of those increased without increasing a lot of weight. And these additives are 3/10, 0.3 of the total epoxy weight. So that's, 3/10 of 1%. Yeah, not 3/10 of the weight, 3/10 of 1%. So it's a small amount of additive to get a significant increase, like a 20% increase in stiffness and impact resistance. Like, wow, that's a pretty good trade. And there's another additive that'll get you that same performance for 1/10 of 1%, the tiny amount. One's a little more expensive than the other. Now, in the article, they're pretty clear on, well, we've tested it very carefully. It's a bunch of engineers overseas that are doing it, and it proves out in the lab. It is stronger, stiffer, and more durable. Nobody seems to know exactly how it works. There's speculation on that the additives affect the uh, intermolecular bonding of the epoxy resin, but I haven't run across an article where anybody's got it pinned down definitively as to the exact chemistry and mechanics that are going on to get these improvements. But I thought I'd try them out. I thought, wow, for a little tiny bit more weight, a little bit more money, I could greatly improve my aircraft. Now, the additives are both surprising and not surprising. When I read about the first one, they were talking about bentonite this, bentonite that. And I go, bentonite? That's what I use for making wine. That's a clay. It's dirt. It's clay that I add to my wine to clarify the wine, to collect the particles that are in suspension, pull them out of suspension, take them to the bottom of the barrel, and get rid of them. And who would put dirt in their epoxy resin? And as I read further, they actually start calling it bentonite clay, and they were serious about it. Bentonite clay, and they think it's the silica particles in the bentonite clay that help with the intermolecular bonds within the epoxy resin. Speculation, but bentonite clay cheap. Look, you get a big bag of it like this, and I'd open this up, but we'd have kind of reddish dust all over the place. Some people strangely use this as some type of health food additive. I don't think I'd be drinking bentonite clay, but I hear some people do that. This is 2 pounds, cost $11. 2 pounds would last you for several aircraft because you don't put much in the resin. And I thought, oh, how interesting. Well, it's cheap. I'll try it out. And the other one that was mentioned in the article is this lovely stuff here. And I'm going to dip my finger in here and show it to you. There it is. Right there. I'll hold out my finger and you go, Raul, that's carbon dust. That's charcoal. And I go, well, that's what it looks like, but that's not what it is. These are carbon fiber nanotubes. You heard that right. You need a scanning electron microscope practically to see them. They're single surface or single layer carbon fiber nanotubes. They are, if I understand this correctly, they're 1 atom thick. The wall thickness is 1 atom thick. And what you end up with is kind of a modified version of a buckyball, except they're tubes with round ends on them. When they draw them, they look a little bit like gram-negative bacteria, same kind of shape. Here's the difference between these two items. You don't need nearly this. You need 0.3 of 1%. This one you need like 1/10 of 1%. Tiny amount. Doesn't weigh much, so the volume is a little bit higher. But this was $11 for 2 pounds, and this is like buying drugs. This is 10 grams for $50. 10 grams for $50. So if you make your panels out of this stuff, you essentially double the cost of your panel that you're making. But given the improvement in performance that they're quoting, well, it's an aircraft. We spend more money to get the performance we need. But talk about expensive. This stuff's expensive. And that pricing that I gave you is for the laboratory seconds. If you buy laboratory grade of this, we won't even talk about the cost of that. So I made up panels. Okay, what do I got? Let's start at the beginning here. 1 layer of 120 Kevlar over the 3/32 inch, 3 pound per cubic foot PVC foam, Arex foam. This weighs 0.28 ounces, just over a 1/4 ounce for this 6x6 panel. And I laid up all of these essentially at the same time so that my hand was doing the same thing, using about the same amount of resin, and trying to be very careful about that. Now, I didn't bother putting any on the backside. It's kind of pointless, This gives us a good example of how much resin is going to go into the foam and what it comes out like. This is actually a pretty nice panel. And then I used my highly calibrated thumbnail to make dents in it. And I go, well, that's better than the fiberglass, but not much. 1 layer Kevlar. In my world, I'd call it the same. But it's half the weight. This is half the weight of the fiberglass for 1 layer of this. 1 layer of the fiberglass I showed you, twice the weight, almost twice the weight. And the dent resistance, it's not worse here. It might actually be a little bit better. So 0.28 ounces for that. And then I did 2 layers of 120 Kevlar, and same layup, but 2 layers of Kevlar, and that's 0.6 ounces. This is essentially the layup they have on the outside of the Swift, or on the early Swifts. I don't know what they're doing on the Swift 3 version. And this is practically bulletproof for denting. I can make a mark, but it bounces back. It's Kevlar, you know. Kevlar has that amazing ability to bounce back. So for double the weight for a given area, you can have something that's essentially bulletproof in terms of dents and so forth, which you dearly love to have on this thing because you don't want any dents in the surface. But is this really needed out on the wingtips that are traveling in padded bags? I don't know. Not clear on that one. And the only way to find out is to actually try it. Build them, try it, and see how they hold up. Then the other two, here's 1 layer, 120 Kevlar, and it has 0.3% by weight of bentonite clay in it, and you can tell that it's a different color. So that bentonite clay is in there. You see it's a little darker, and so it's the same layout. The resin doesn't impregnate the fabric as easily. It doesn't spread out as easily because of the clay that's in it, even though it's a tiny amount. This weighs 0.39 ounces, so we were at 0.28, and for an additional 0.11 ounce, in other words, essentially 1/10 of an ounce, you get the added durability from the clay and bending stiffness. And I'll tell you, this is, I put down this other one. If I actually had weights here and so forth, I could show you, but this one here is more flexible than this one. This one is definitely stiffer. Is that going to make a big difference for me? I don't know. Is it enough to be worth the trouble and the cost? The cost is negligible. It's not that much stiffer. And then I tried denting. There's no difference. Impact resistance and dent resistance, probably 2 different things, especially the kind of denting I run into. And I did not find any significant difference between the 1 layer Kevlar with no clay and the 1 layer Kevlar with the clay. Now, it could be a case that the research that they're doing involves multiple layers of fabric, in which case they might be getting effects in the chemistry and the chemical structure and so forth, mechanical structure, where they get benefits that I don't get with just 1 layer. I don't know. But for the added trouble of having to mix in the clay and the added difficulty of impregnating the cloth and spreading it out, not worth it. It's heavier, and it doesn't buy any significant increase in performance in terms of denting. The difference between these two, where I made the dents, is negligible. So, as cool as it sounded, that one's out. Now, carbon nanotubes. Now we're talking high tech. Stuff that's been invented since the Swift was created. So it's got to be good, right? It's new technology. It's space-agey stuff. Carbon nanotubes. Incredibly strong, especially in tension. And it doesn't take much. Just a little dash of go in here. And you see it comes out and it almost looks like carbon fiber cloth, which sort of makes sense. Not as dark. This stuff was pretty easy to work with. You add it in there, spreads out the same. So almost like, the only difference is you can't really visually inspect this very well about how well are you bounded to the foam. So you have a little loss there in terms of its buildability. Difficult to visually inspect the quality of the layout. And then I looked at bending, bend this one. It's about like the bentonite clay one, just a little bit stiffer, not a whole lot. If I play with them here, I can tell there's ever so slight more stiffness on this. And now down to what really counts. What we really wanted to see was the dent resistance. And you know what? Oh, no difference. It's about the same as the bentonite clay one. Ever so slightly better than the 1 layer Kevlar. But massively more expensive. A little aside there. No, not worth the trouble. As cool as it sounds, man, if I was marketing this stuff, I say, my aircraft's built with carbon nanotubes, and people are, ooh, that's cool. But Didn't buy me anything. So that's out. So we're back to one layer of 120 Kevlar, and it has about the same dent resistance as the fiberglass, but the darn wing is transported in a bag. We haven't had really any problems at all with dents in the outer wing panels. So one layer of Kevlar is probably going to be good enough, and it'll be half the weight of the fiberglass, which would be super, because there's a lot of area in this tube here, this D-tube area. We got all of this area and all of this area, and it's going to save 3 or 4 ounces, if not more, 5, 6. So out of the pound that I want to save, a good portion of it is this, and that goes right back to the weight's driven by the skins. So if I can save weight here, yahoo. Okay, so now the other thing we need to talk about. So we've decided on the fancy materials are out, despite what the research is showing, and because we got a very special problem here. The old-fashioned way seems to work just as good as the new stuff. So we're down to this guy here and the spar. Now you know that not only the spar gets bonded in here, build the spar, build the D-tube, and then I bond the spar in like this. Another second, sorry if I went out of frame. Another secondary bond, put the spar in here like this. Can you build the spar and the D-tube all at once? I don't know, I've never tried it. I don't think I'd care to try it. So it's always going to be a secondary bond. Always a secondary bond. Now, what about the margin on margin? Remember I mentioned that these skins, these 2 skins here, can take a tremendous amount of bending load. But they're not in my calculations. Just the spar caps. Just those unidirectional carbon fiber spar caps, they have to carry all of the bending loads in my calculations. And these guys, these skins are all margin. The spar caps on that spar that I showed you will carry about pretty close to 30,000 pounds in tension. That's a lot. Well, when I went in and calculated, what if I have 2 layers of Kevlar? One on the inside, one on the outside. No, excuse me. I did it for 3. So I got 3 layers of Kevlar, and I calculated it was 24,000 pounds. Just the D-tube alone with the 3 layers of Kevlar will take almost as much load as those carbon fiber caps. Well, I don't need those carbon fiber caps then, do I? How much do they weigh? Well, several ounces. 3 ounces, 4 ounces, something like that. And the wood that's there on that one, well, golly, that's not needed at all for strength. That wood is there just to prevent the carbon cap strips from buckling. But with the new spar that I'm talking about, the new spar that wraps around like this is curved, and the Kevlar will come together into a flange, it's not going to buckle. It can't buckle. It's glued to the D-tube. So those flanges glued to the D-tube, and I don't have to worry about these cap strips buckling. Because the D-tube would have to buckle, and if the D-tube buckles, well, you've got bigger problems in your hands. So the wood is overkill. The wood's really here just to make it buildable. But if I'm molding the spar, I don't need that. So the wood's out. The wood's 2-3 ounces. Get that out. I think I can remove all of the spar cap and put in some just maybe 1 or 2 layers of standard unidirectional carbon fiber between the 2 layers of Kevlar for the flange here. Now, what I have to go back and calculate or do a guess at is, hey, look, this spar, even no cap strips, just assume it has no cap strips, and this shear web is prevented from buckling or twisting, which it is when it's bonded to the D-tube, because it's a whole big round tube. This carries bending loads also, not included in the calculations. Only the cap strips are in my calculations. So there's a whole bunch of material here, skins, wood caps, shear web, that are all strong materials that are not included in my bending calculations. I only put in these cap strips. A lot of margin on margin. So I'm going to go back and revisit the calculations, try to do an estimate on what kind of bending loads this shear web will take, and redo calculations on the D2, how much bending load that'll take. And then I'll add in back in a skosh of margin, probably by putting some unidirectional in the flanges of the new spars. And I think that this guy's, the new spar will come out, I'll bet you right now, when I build the new spars, even with the fittings, all the changes that I'm going to make, it'll weigh pretty close to half of what this one weighs and be strong enough, plenty strong enough. And the D2 skins, probably going to drop those by at least a third, maybe more. So that whole thing weighed, what did this thing weigh? It says 2.5 ounces per square foot. The whole thing weighs just over a pound. 17.5 ounces for the whole thing. Now, the other thing that I'm going to do to improve the performance of the D2, if you've been with me for a while and you know what I'm doing here, I'm doing something very unusual. The inner skin and the outer skin are not bonded together. It's just the foam. This gets trimmed off here for final fit, and the outer skin and the inner skin are not joined together. And that's because I set these up so that the inner skin is designed to carry all the loads, and the outer skin was just there for durability and aerodynamics. So that's another margin on margin thing, because the shear loads can be carried through the foam. You don't necessarily have to glue the two skins together. You can't carry as much, but you can carry enough. And so I have to include in the calculations this outer skin. I'm going to go do that. Torsional loads are low. I think by the time the skins are strong enough to carry the bending loads, they're way more than strong enough to carry the torsional loads also. Very low torsion out at the wingtips. So what I'm going to do is, instead of foam here, at the end of this foam, the foam's going to come here and be butted into some balsa wood. And I'm going to put in a sheet of balsa in here, 3/32 of an inch thick. And when I make the trim for final fit, the trim will be in the balsa. And the outer skin and inner skins will be bonded to the balsa wood. And the balsa wood will carry maybe an order of magnitude more shear than the foam. It'll be equivalent to having the outer skin and the inner skin bonded to each other. The wood will carry all of the shear loads that are required to be carried, and then some. So I'm going to increase the bending strength of the D2 by putting in a balsa strip here. And I'm going to make it wide enough because you don't know exactly where the trim line is going to be, but you only need just a thin strip of balsa to bond the inner and outer skins together. So that'll be another change. That's a little bit more complex on the buildability issue, but it's not that bad. I've made some samples that way, and it's pretty easy to do. You just glue the balsa to the PVC foam before you do the layup, and it works out pretty good. If you're really tricky and careful on how you do the layup, you can actually use the resin from the layup to glue the balsa to the foam. But I found overall it's a little easier to just glue them together ahead of time with a little bit of epoxy, or you could use urethane or anything like that. It's a thin line, and then you have to sand it smooth after they're bonded together because you never get it exactly flat. So a little bit more complexity on build, but a lot more strength in terms of distributing the loads between the inner skin and the outer skin and how much load it will actually carry. So there's a plethora of ideas. Some of them have stood the test and come out at the other end, and we're going to apply them. And there's probably a dozen different things that I'm doing. Little by little, we'll get that pound out. And if I'm really lucky, I might get out more than a pound. And if I get a pound out of each wingtip, well, that's 2 pounds. That's half the weight of the new elevons that I put on there. And I'm good then. I've saved that weight. And I'm taking some weight out on some other things like wheels and so forth. That's helping. So there we go. That's the results of a month's worth of trade studies and parametric studies and a lot of thinking that went into this. I hope that you have found the information to be useful. You might be surprised. You might find it useful years from now. And stick with me. We're waiting for Labor Day here, where right after Labor Day, they take the lifeguard station down at Marina Beach, and I'll be able to get back out there. The glider is ready now for flying. Or if it gets a little cooler, if we get below 100 degrees, we'll go back to El Mirage and we'll try some more towing there. But right now, we're waiting for one of the 2 test sites to be amenable to further test flying. And while I'm waiting for that, I'll be building new wingtip panels. And in the meantime, hang in there with me, no pun intended. And as I always say, fly safe and bye for now.